Okay, it looks like the number of people joining has steadied. So I'm going to go ahead and get us started. Thank you everyone for joining. We're really excited to be continuing this webinar series. Before we begin, I just want to make sure everyone's aware of the chat and Q&A features. If you have a question during the talk, feel free to um, jot it down in either one of those message boards, and we will get to it at the end of the talk. I also want to remind everyone that if you want to suggest future speakers in this series, we have a suggestion form on our website, and I'll put the link to that in the chat right now. So without further ado, Dr. Peter Barry is a tenured associate scientist at the Woods Hole Oceanographic Institution, where he studies volatile cycling between deep and shallow terrestrial reservoirs and aims to understand the processes that determine the distribution of volatiles, both today and in the past. Today, he will be discussing the volatile characteristics of the Central and South American volcanic and geothermal systems. We're really excited to have him here. And without further ado, the floor is yours.
Great, thanks so much. It's awesome to be here and talk a little bit about my research. So I'm going to talk about some studies that we've recently done in Central and South America. And I just want to acknowledge before I get started, some of my funders, the National Science Foundation and the Deep Carbon Observatory, which kind of funded some of the initial work in this area. So to just kind of jump into things, if I zoom out like really big picture, you can ignore all the words on this, but I just want you to look at this evolution of how Earth evolved. So if I zoom out like big picture, what am I interested in as a scientist? Well, I'm interested in how the Earth was initially formed and how it acquired its volatiles. So elements like water and carbon and nitrogen, the elements that initially formed our planet, and how we eventually developed plate tectonics. And then, now we have a planet which is rich in volatiles like water at the surface, and it obviously sustains life because we all live here on planet Earth. So I'm sort of interested in this big picture evolution. Um, More specifically, I'm interested in cycles of volatiles. So one of the things I study is carbon. So I study the deep carbon cycle. So I think a lot of people are probably familiar with the surface carbon cycle. But this is like a much deeper cycle that involves plate tectonics. And what I try to do is I try to constrain, basically how much carbon is coming out at different volcanic settings around the world. So these are estimates from a review paper from about 10 years ago. And these are estimates in megatons per year of how much carbon is being emitted from mid-ocean ridges, from arc volcanoes, and then comparing that with how much carbon is being subducted back into the Earth's interior due to subduction processes. One of the big unknowns is, how much carbon is basically stored in Earth's crust. And you can see that there's a huge uncertainty here on like the solid storage in Earth's crust, somewhere between 0 and 47 megatons. So it's just a really poorly constrained system, like this deep carbon cycling process. So to get after that, so like how do we understand and study volatile cycling and subduction zones? Well, we actually go to subduction zones, and today I'm going to talk about work that we've done in Central America, in Costa Rica, and then some work in South America, in Chile, Argentina, and Peru. But what we do is we go and we try to actually make measurements of volcanic plumes as the gases are erupting. We also go into active volcanoes, and this is my colleagues and I like collecting samples from these fumarolic gases inside of Poas volcano in Costa Rica, so we can actually make a direct measurement of how much carbon, water, noble gases, everything that's coming out of these actively erupting systems. Importantly, we also work in the Forearc region. So the Forearc region, if you think about this, is the subduction zone, so the plate's going down this way. We have our active volcanic front here. Well, there's a lot of geothermal manifestations that are present in the Forearc region as well as the Backarc region, but we're actually interested in collecting these gas and water samples in the Forearc, and that's an important component, turns out, to the total flux of carbon and other volatile elements. And then we compare with those emissions of what's coming out with, we can leverage, data that's from from the drilling program, basically. So there's estimates of what the sediment package, what that downgoing slab actually looks like, and we can leverage existing knowledge about what's being subducted into the system. So we basically have a mass balance of what's going in and what's coming out. And so first, I'm going to talk about a paper we published a couple of years ago now, 5 or 6 years ago, and it was work that we were doing in Costa Rica. So this is where Costa Rica is located in Central America, and we just zoom in on that area. I wanted to point out a few things. Here's like the volcanic arc front. So these symbols here that look like volcanoes are where there's active volcanoes in the region. This is where the trench is. So this is where the plate is actually, the plates are colliding and you have subduction heading this way. And one of the really unique features about Costa Rica is there's this very prominent on-land Forearc region. So you can see that we can actually have access to the Forearc region because the Nicoya Peninsula here, which is relatively close to the trench. So we're able to actually go out to the Forearc and sample on land, which is a big advantage. So we can kind of probe what's happening in this lower temperature Forearc region. We collected about 20 samples. The blue symbols are from sort of this northern region, and the orange symbols are from the central region. And those symbols will be consistent throughout the first part of this talk today. Yeah, so this is looking at the helium isotopes as a function of distance from the trench. And so we're basically traveling from the lower temperature Forearc all the way to the volcanic arc front. So we're going from these low temperature manifestations to like actively erupting volcanoes. And I'll give everyone a little bit of an overview on helium as a tracer because I think about helium all the time because I'm a noble gas geochemist, but I realize that lots of folks probably don't think about helium that much. So if we have like a cross section of the Earth here and we think about where helium isotopes are coming from, well, helium has two stable isotopes, helium-3 and helium-4. Helium-3 is primordial, so that's like left over from when the Earth accreted. So it's a very primitive primordial signature, whereas helium-4 is continuously produced due to radiogenic decay of uranium and thorium. So it's produced everywhere, both in the mantle, but especially in the crust where there's lots of uranium and thorium. When we look at the 3-4 ratio, we look at it as like a ratio that we measure in a given sample relative to air. So by definition, when we talk about 3-4 ratios, air is defined as 1 because everything is normalized to air. When we go to Earth's crust, because there's so much uranium and thorium that's decaying to produce all this radiogenic helium-4, the 3-4 ratios that we measure in Earth's crust are very low, about 100 times lower than the air value. And if we go and we sample a mid-ocean ridge or the well-mixed sort of upper mantle reservoirs, we consistently everywhere in the world measure a 3-4 ratio around 8 times the atmospheric value. And if you go to places like Hawaii or Iceland that are influenced by like a mantle plume, we often measure 3-4 ratios that are much, much higher, up to about 50 times the atmospheric value. And this is because we're tapping into this deeper primordial source. So the relative amount of helium-3 is much, much greater. And then what I'll be talking about today is volcanic arcs, and the typical volcanic arc value is slightly lower than MORB, somewhere around 5.5, 5.4. So if we come back to this very first plot that I was showing, just distance from the trench versus the 3-4 ratio, you can see, maybe not surprisingly, in the arc front, we measure values right around 6 times the atmospheric value, and that's typical of a volcanic arc. And when we're in the Forearc, we're measuring values you can see that are much closer to around 1, which is actually the atmospheric value. So we're measuring everything from very low, kind of, even some of these are lower, these are like crustal values, up to typical arc values for helium isotopes. But the ones that are close to 1 are not just air-saturated water in the subsurface. In fact, we can look at the helium isotope ratio again versus the helium to neon ratio, for instance. And we can plot where air plots, and plots right around 1. And we can see that there's many samples from this study in particular that have 3-4 ratios that are close to 1, but they have big helium to neon anomalies. So this is indicating to us, to a first order, that these are not just atmosphere. These are actually deep sourced signals from the mantle and from the crust, and they just happen to plot close to 1. If they were, in fact, just atmospheric, they would all plot on top of this red star. So this is a really important bit of information. And then you can see, of course, some of these samples have values up to 6, 6.5, nearly 7 times the atmospheric ratio, and those also are accompanied by these enrichments in helium to neon. So I'll show you this plot a couple times because I'm going to talk about a couple different studies. So I'll keep coming back to this. But for this first part, you just remember that these are many of the Forearc samples. We also measured carbon. So because that was the kind of the question that I set out to answer at the beginning of the talk about yeah, like how is carbon move between these deep reservoirs? And here I'm plotting carbon isotopes as a function of DIC concentration. So these are the closed symbols are water samples. These open symbols are actually gas samples. And this really kind of remarkable trend popped out when we plotted the data from Costa Rica. You know, the samples that were from the arc front plotted up here, and they had typical values. The mantle value somewhere around -5. So the gases, volcanic gases from the volcanoes themselves, are plotting right around the mantle value. So that makes sense. But as we move, as we move to the Forearc region, so these are like this is the volcanic arc here, and these are all kind of arc samples. And then as we move into the Forearc and then the outer Forearc, so the area that's closest to the trench, we actually observed systematically, we saw the lowest carbon isotope values in the outer Forearc region. We thought that was really interesting. So if we think about like what the sources are of like what's coming in, we can go back to, we think of what's coming out of the volcano as basically a direct conduit of coming from the mantle, and the mantle is mixing with material that's being released from the subducted slab. You can see there's a distinction between the northern and central samples. So somewhere between about +5 to about very close to 0. These are the actual values. And the way that we explained this was we were able to model it as the amount of carbon that was actually pulled out of the system. So we modeled this as calcite precipitation. So if you have release from the downgoing slab, and that carbon is effectively sequestered, well, there's going to be a fractionation associated. And the residual fluids that you measure at the surface are highly fractionated. So you can see that in the outer Forearc samples, we're estimating that, up to about 90% of the carbon may have been pulled out of these fluid samples. Okay, so here's like a cartoon just trying to show you exactly the same thing of we have carbon that's coming from, it's a mix between the slab and the mantle, and that's being released. We measure isotopically low values for DIC and DOC in the Forearc region. And then we can construct a model that estimates based on, the extent of fractionation between calcite and water, how much carbon actually would need to be removed. And again, we estimated it's about 90% of the carbon here in the study in Costa Rica. 92% is actually sequestered as calcite, according to this model. And you might think, okay, cool. Well, why is that important? Well, when we think about volatile fluxes and the mass balance at subduction zones, we would typically use like a cartoon like this or a mass balance like this. So we know again from like those IODP drilling constraints, we know how much carbon is in the sediments in the downgoing slab. And so that's our starting number. We from our direct measurements from remote sensing and from being in the volcanoes, we have an estimate of how much carbon per year is being fluxed out of those volcanoes. And before this study, basically you would take the input minus the output, and any difference between these two numbers, presumably that was the amount that was being subducted past the volcanic front and being transported into the mantle for deep long-term storage. But this study, we were again focusing on the Forearc and the outer Forearc region, and we were able to estimate and quantify how much carbon is actually bound up in that solid storage in the crust due to a process like calcite precipitation. And this kind of fundamentally changes the math on, how much carbon makes it down into the mantle. So based on this study, about 20% less carbon is making it to the deep mantle, which is a pretty big number. So this was an exciting finding from this very first study that we did. So I just want to summarize really quickly, like the findings from this study. We observed that the carbon isotopes are fractionated, and we proposed that this is due to calcite precipitation. We estimated based on the model, the calcite precipitation model, that about 92% of the carbon is sequestered in the Forearc of Costa Rica. And it suggests that the Forearc is in fact a really important sink for carbon and fundamentally changes how we think about the mass balance. So that was the first part of my talk, and again, really focused on the Forearc region. And I want to talk about similar studies now that, based off this work, we conducted in the Andean Convergent Margin. So yeah, one of the first things after we published that paper back in 2019 was, how pervasive is this? Do we see this in other subduction zones? Do we see this not only in forearcs? Do we see similar processes in volcanic back arcs? So we thought the Andes would be a great place to work. There's obviously, thousands of miles of an active volcanic front. It's basically split into the we were working in the Central Volcanic Zone and the Southern Volcanic Zone. There is the Northern Volcanic Zone up here. Um, and really, this is actually this is a figure that's from the NSF proposal that we wrote back in like 2021 to continue this work in the Andes. And yeah, I'm just showing different sort of tectonic features and subduction parameters. So here, like all the gray symbols are where there's active volcanoes. So here I'm showing like the offshore sediment thickness. So we were hypothesizing that things like the amount of sediments being subducted into the system could affect the volatile output that we saw. Um, we also hypothesized that the subduction angle, you can see it's much different between the central and southern volcanic zone. The angle of subduction changes pretty drastically. And then what's also very important is the overriding crustal thickness. So this is the thickness of the crust on the continent itself. And really, it's a really pretty stark contrast between the central volcanic zone and the southern volcanic zone, where you can see that the crustal thickness in the central volcanic zone is up to about 70 kilometers thick, which is extremely thick relative to other subduction zones around the world. So these were the sort of the hypotheses that we laid out, that these sort of large scale geodynamic tectonic features would influence what we saw in the volcanic gas emissions. Okay, so just zooming in now on the central volcanic zone and the southern volcanic zone of Chile and Argentina. Now I'm showing where the active volcanoes are as these red triangles, and then you can see these blue points and these blue circles, sorry, and the orange circles are where we collected samples in both regions. So we collected well over 100 samples over the course of doing, I think, 4 different field campaigns. Yeah, and here's some pictures of like what it actually looks like. And again, we were focused in large part, I'm just going to flip back to the map, on the back arc. So you can see here's the subduction is going this way. We have the plate sliding underneath South America. There's where the volcanoes are. There's not many active Forearc samples, but there's all these geothermal hot springs and cold springs in the back arc. So this is sort of what a lot of them look like. They're generally pretty low temperature, somewhere between ambient air temperature, 10, 15 degrees, up to maybe 50 or 60 degrees in the back arc region. And it's, yeah, just an incredible place to do field work. Right. So we also were working in the volcanic arc front. So some of these samples were collected from like fumaroles themselves. Like at this is a short video. I have a little time lapse video if I can get it to play. Oh yeah, there we go. So this is Ulca volcano, which is in sort of northern Chile, and we were sampling very close to 18,000 feet. So yeah, I mean it's about 5,200 meters. It was extremely high elevation. And I was taking this video, but that's actually me standing there not doing very much at all because I was feeling quite a bit of altitude sickness, believe it or not, that day. But you can see our team like actively running around and collecting these gas samples from the vents themselves. Okay, cool. So we visited like approximately 100 different places, and now I'm plotting the helium isotopes again versus helium neon. So this is the same plot that I showed you for Costa Rica. To a first order, you can see that not many of the samples at all plot close to air. We see large deviations in helium isotopes everywhere between crustal values and mantle values. And we see big deviations in the helium to neon ratio, which is indicating that these are deeply sourced fluids and gases. If you kind of squint and just look at the blue samples, which are from the Central Volcanic Zone, and the Southern Volcanic Zone samples, which are the orange symbols, you can see there's a pretty stark difference in how much of the helium, at least, is coming from the crust and the mantle. So if we assume like a binary mixing relationship between mantle and crust, we can estimate on average for the orange Southern Volcanic Zone samples, about 62% coming of the helium's coming from the mantle, about 38% coming from the crust. And then for the central, excuse me, for the Central Volcanic Zone, it's about 80% crustal and only about 21% mantle-derived helium. if we return to like how I set this up, is that we were looking at, these big geodynamic differences between the settings. Really want to highlight this. So the Central Volcanic Zone samples were predominantly crustal, and these are the samples that have this really, really thick anomalous crust. So this really made sense to us that we would see crustal-like helium samples where you have anomalously thick crust. We were also interested in the processes like calcite precipitation, and we measured carbon isotopes just like we did. I'm plotting it a little bit differently than I did in Costa Rica. Here I'm plotting the carbon to helium ratio, CO2 helium-3 ratio versus carbon isotopes. You can see that the vast majority of the samples can be explained by mixing between sort of the Earth's mantle and then some sort of subduction component like sediments that were subducted or limestone that was subducted. But some of the samples have lower carbon to helium-3 ratios. And this is indicating that perhaps some of the carbon has been pulled out, again, due to a process like calcite precipitation. And that's actually a temperature-dependent fractionation. So you can draw a line from a starting composition out, and you can model the temperature at which this calcite precipitation likely occurred. But importantly, we didn't really see any systematic changes like we saw in Costa Rica, where it was this really beautiful Raleigh distillation trend like we saw in Costa Rica that allowed us to quantify how much carbon was being pulled out. Here, it kind of looks more like a shotgun. So it seems like there's not a really coherent trend in the back arc. Okay, cool. So I just want to summarize our findings from the second part of the talk. The helium isotopes increase to the south. So the highest values we see for helium isotopes, the most mantle-like values, are from the Southern Volcanic Zone, and they plot close to like the typical arc M member globally. The lower 3-4 ratios are found in the Central Volcanic Zone, suggesting there's more crustal contributions. About 80% of the helium comes from the crust, versus only 78% is coming from the crust in the Southern Volcanic Zone. Again, this is totally consistent with what we see in the crustal thickness between the two regions. And we concluded that crustal thickness exerts a primary control on the extent of fluid-crust interaction. We did see lower carbon isotopes and lower carbon helium-3 ratios, which is consistent with calcite precipitation. But again, there was no real quantitative calcite precipitation trend like we saw in the Costa Rica study. Okay, so far I've shown you some of the results that we published in this 2023 Frontiers paper. And you can see that there's tons of, this is by no means only my work. I was the lead author on all 3 papers that I'm going to present today, but there's a huge team of folks, too many to think. But I'll try to think a few now. So I'm showing where we collected samples in 2019, in this sort of lighter shade of blue, and in 2020. But we also went back in 2022 and we collected samples in near Peru and in northern Chile. And in 2023, we were in the back arc of Argentina. And I want to highlight these 2 students who both visited my lab as summer student fellows, and they both analyzed these samples, and they contributed to the paper that we published earlier this year. And yeah, so these students, both Cassandra and Kieran, were really amazing in the lab, and they're now both, after they came as undergrads to visit my lab and work in the lab, but now Cassandra's doing a PhD at MIT Hui Joint Program, and Kieran is doing a PhD at Brown University. So really sort of thrilled to see them, get some lab experience in my lab and then go on to do PhDs and such amazing things. Cool. Yeah. So like so there's basically 4 field campaigns. The first 2 field campaigns were in this first paper. And then I'm going to talk briefly about results from the 2022 and 23 field campaigns, which came out in this EPSL paper that we published just earlier this year. Okay, so here's the locations of the 2022 and 2023 samples. Again, you can see, some are from Peru, many are from northern Chile, and then we have, a whole handful from the back arc of Argentina. And we can make exactly the same plot that we made before of helium isotopes versus helium neon. And we can see that everything can be explained by mixing between crust and mantle. And we can actually see that the delineation between how much of the helium is coming from crustal sources versus mantle sources agrees really, really well with our previous findings. So, we published the paper 3 years before, and we found 79% crustal contribution for helium in completely unique samples. So I should emphasize that these are like 100 different sites and thermal springs that we visited for this new study. We also measured carbon isotopes, and again, it's a similar story that most of our data can be explained by this three-component mixing between the mantle, sediments, and limestone, and then there's maybe some indication of calcite precipitation. So you're probably asking yourself, okay, so what's new? Why did this warrant a completely new paper in 2025? It looks like the results are almost identical to the 2022 results. Well, we did a few additional things. We also measured radiocarbon in all the fluid samples that we collected, and I find these results to be really, really cool. Okay, so if we look here, this is radiocarbon plotted versus helium isotopes, and this is radiocarbon versus the helium to neon ratio. And I've shown both of these ratios several times already in this talk. So you can think about like the fraction modern carbon as being basically if the activity of radiocarbon was 1, that would mean that water was in contact with the surface like yesterday, and that's like very modern water. And if you measure activity of 0, that means that it's older than 45,000 to 50,000 years. So it's very old water. And we saw sort of this like very cool bimodal relationship when we plotted radiocarbon versus helium isotopes. We saw that as soon as we got above about 1.8 Ra, every sample that we measured was completely radiocarbon dead, meaning that it was a very old fluid. So if we saw any helium anomaly, it was a strong indicator that we were sampling deep fluids, which would be in line with our hypothesis that we think if we're measuring helium anomalies in these systems, that these are deep source signals. These are not superficial signals. And likewise, we saw that the 3-4 ratio around 1 Ra, which is the atmospheric value, was kind of all over the place from old to modern values. When you look at the same thing of radiocarbon here versus the helium to neon ratio, the relationship's even more stark, that we see sort of this cutoff around 2, and everything above 2 is for the 420 ratio is radiocarbon dead. So it's indicating to me that any sample anywhere that we go in the world, there's a strong likelihood that if I've measured a helium to neon anomaly above 2, that's indicating that's a deep fluid. Those are not related to a surface signal in any way, shape, or form. And so why is that important? Well, if we rewind to like the very beginning of the talk when I was talking about the work we had done in Costa Rica, this was sort of like the key plot that formed our whole model. So we had this like sequestration model for calcite. And this is like the really key plot. And people would say often to us when we first published this paper, they would come up to me at a conference if I was giving a poster or a talk, and they would say, I don't know, Pete, I don't really believe it. I think that you're just seeing, biogenic material. So we're seeing like leaves from the surface and organic material that's seeping down into the groundwater system. And that's about minus 25 per mil for carbon isotopes. So I don't actually think this is a fractionation trend. I think this is a surface trend. And we would always argue with them and say, no, we don't think that these are like surface features because we see, yes, we see air like helium isotopes. We see these big helium to neon anomalies somewhere between 2 and 10. And so these radiocarbon data that we have here is confirming that, in fact, these are ancient features. These are old, deep source features. So this was really exciting result for us to get because it was really confirming our assumptions from years of work that everything that we were looking at was a deep feature and not related to just a surface signature. Okay. Yeah, last couple slides here, and then I'll open it up for questions. Again, this were all the samples that we collected in 2022 and 2023. And there's one sample that we were able to target for initial analysis. It's this PI sample here, and it's really close to, and it's unique. Okay, so it's unique. It's in the sort of back arc of Argentina. So the volcanic arc front is kind of coming down like this. So this is a back arc sample. It's located on top of this Altiplano Puna magma body, which is a huge magma body, which is sitting below the crust in this part of the world. It's about 200 kilometers in diameter. It's approximately 11 kilometers thick. Um, and it's about 15 to 20 kilometers below the surface. And it's the largest known magma body in the world. So there's just this huge magma body sitting underneath the very thick crust that exists in the Central Volcanic Zone. And I said this sample is anomalous. Well, if we look at like the helium isotopes, and this time I'm plotting helium isotopes versus argon isotopes, and here's all the samples from Argentina and Peru, you can see that this PI sample plots way out here. It has a really large argon isotope anomaly. Um, and so it has argon isotopes somewhere around 500. And so that's air plots here. So it's like, you know, air is 300. And you can see that most of the samples for their isotope signatures are close to air with respect to argon. This has a big anomaly. It has a low helium-3, helium-4 ratio of about 1.32. So again, a low 3-4 ratio is indicating that it's predominantly crustal. So that's what we know about the sample. And then we were able to, based on the fact that it had this big argon anomaly, we were able to target it for high precision xenon isotope work. And this is work that we did here at HUI in Alan Seltzer's lab. And he developed a method using a dual inlet mass spectrometer where you can actually measure xenon isotopes at very high precision. So improving on the precision that we can measure on a noble gas mass spectrometer, probably by up to 2 orders of magnitude higher precision. So it gives you all this resolution into what's happening with xenon isotopes. So there's 9 stable isotopes of xenon. I'm sure that if anyone has questions about xenon, we can go into all the details later. But just to like a first order, the heavier isotopes are related to crustal physiogenic decay. So basically like a radiogenic decay, and then you have the 129 signal, which is related to the mantle. So in a similar way that you can look at the 3-4 ratio, you can look at the 129 to 136 ratio, and that's going to tell you about how much of that xenon is coming from the mantle and how much is coming from the crust. So this particular sample, this PI sample, had like 84% crustal helium. And when we do the completely independent calculation using xenon, we see that it has about 88% crustal xenon. So what we're seeing here for the first time, because this is the first time that we've measured high precision xenon isotopes in a volcanic gas like this, we're seeing this sort of coupled release of all the noble gases. So, or at least helium and xenon are being released together. And we think it's related to bulk degassing of the crust rather than um, melting or low temperature diffusive loss. So you have, a really small atom of helium being released at the same rate as a much larger atom of xenon. So for us, this was like a really cool result. And I can stop there and take questions, but it looks like I have, maybe like 5. I can talk for like 5 more minutes just to, you know, wrap up on the studies in Central and South America, but also talk about, some of the ongoing work that's going on in my lab. And if you're interested in this, I again be happy to talk to anyone after the call. So we've done all this work in subduction zones. You might ask, like, well, what's next for the research questions? We're interested in studying more Forearcs, so systems that are analogous to Costa Rica. If you remember, I said that we were targeting working in Costa Rica because it had a prominent on-land Forearc. Most of the Forearc regions in the world are in submarine settings. So we just this last December, so about almost exactly a year ago, we were on a research vessel above the Mariana Forearc region, and we were diving to the seafloor at about 1,200 meters depth, and there's these boreholes, and we were able to use this remote operated vehicle to go down and collect fluids from these subsurface boreholes, which are telling us about the emissions coming out of the Forearc of the Marianas. And so here's like a little video, and it's sped up, of us actually driving up to these boreholes. And you can see it's like actively, there's fluid coming out. There's brucite, which is precipitating out of these Forearc fluids. And so we're able to kind of go up here, and we use the arm of the submersible to knock some of this brucite that's precipitating off. And then we were able to, lower our sampling tubing down into this borehole and collect these pristine fluids that are emanating out of the Forearc. So these boreholes were like drilled into where there's active serpentinite mud volcanoes. Um, and yeah, this is kind of what our sampling gear looks like. So we have this long tubing here, which we lower into a hole, and then we have these cylinders that we can fill up with fluids, and they can withstand the pressure of coming up from depth to the surface, and then we can measure um, helium, noble gases, carbon, nitrogen, all the fluid chemistry that we measure. And so we have like another constraint on what's happening in the Forearc. Um, yeah, and here's some. This is the again the plot. This is probably like the fourth time I've shown you this plot, but these are some of the preliminary data from the Mariana Forearc region. You could see that yeah, some have helium anomalies, which suggest about 45% helium. Most of the samples suggest about 10% mantle helium. So we're getting a sense for, where the fluids in the different Forearc are coming from and how we can compare that to fluids from like an on-land Forearc, for instance. And we are able to do a similar calculation using those large stainless steel cylinders. We were able to collect enough xenon to do a similar high precision xenon measurement. And then finally, yeah, just wrap up just like the most recent work just earlier this year. We went to New Zealand and we collected about 71 samples. And New Zealand is another place where there's a prominent Forearc region here. There's all these mud volcanoes, and then there's sort of an active rifting area um, around central North Island. And then there's back arc samples out here near New Plymouth. So yeah, we like collected samples from regions like this that were really high temperature boiling sulfuric systems where we could collect gas samples. And there's my sampling equipment. You see it degassing very vigorously. We also visited these mud volcano sites. These are like really low temperature. So this water is like ambient uh, air temperature, like 15 or 20 degrees, and there's kind of mud burping away in these giant mud volcanoes in the Forearc. And then we also visited some wells that look like that.
What was the temperature, Donna?
There's actually like a lot of
What was the
gas
temperature?
coming out. So with that, I will now actually stop talking and open it up for questions. And yeah, hope everyone enjoyed it. If you have questions, let me know.
Thank you so much. What an excellent talk. Let's give everyone a few minutes to type out their questions. As a reminder, you can use the chat or the Q&A feature, either works. So yes, thanks again.
Thanks. I can't see how many people are actually online.
I think we have about 20 synchronous people here right now. And
Great.
then also, as a reminder, we will be uploading this to the YouTube channel. And so if you want to send it to any of your colleagues who weren't able to make it synchronously, anyone can do that. And if you have questions after the fact, just feel free to email us and we will pass those along. Okay, I'm not seeing any questions so far, so maybe everyone is crystal clear about everything that was discussed. Um, in which case we might give everyone 20 minutes back of their morning. And if anyone thinks of anything later, please send us an email.
Yeah.
So Peter, thank you so much for taking the time today for such an excellent talk. Oh, sorry, saying something in the Q&A. Thanks from Martin Coria. Thanks, Peter, for your talk. It seems to me there's any criteria for your sampling based on your methodology or your geological setting. Is there any criteria for sampling based on your methodology or geological setting?
Yeah, so it's a really good question. So yeah, we're interested in, I try to show up like a couple of videos of the kind of places that we would visit. Are typically like thermal hot springs, cold springs, anywhere where we think that there's fluids and gases emanating from depth. And we're working in the forearc, in the arc, in the back arc. We really want to do this. We want to paint a whole picture of like what's happening like across the arc itself. But really, what we're able to measure is the gas chemistry. So we want to collect either gas or water samples. We can get after like the dissolved gases in the water. We can sample the gases directly. That's going to give us some insight into the sources of these fluids.
Great. Thank you. Um, and with that, I think we'll close out this session. Oh, nope, never mind.
Here we go. Okay.
Okay, they're flowing in. Okay, so another follow-up from Martin Correa. Is any minimal amount of samples that you collect during this campaign?
During the campaigns, yeah. Um, well, you could, if I come back to like sort of there was a map that showed everything that we had collected. Like this is like for the study in South America, these are all the sample locations. You can see that like there's well over 100 sampling localities. So this is like a pretty comprehensive regional distribution. So it's really important for us to try to target, if possible, to get samples in the forearc, in the arc itself, and the back arc to form this complete picture. And generally, when we're in like one geographic region, we would probably try to visit like 20 to 30 sites, whatever, as many as we could possibly get to. Typically we'll go for a week or two in one locality, and there's a lot of driving involved, and you're always working with local geologists who kind of have some insight into where these features are. But yeah, I would say, look, yeah, typically to have enough data to write a paper where you kind of want to visit like 20 or more sites in a region. Should I read the next question?
Yeah, from Nick Burley. Any plans to study the situation in Mexico where the changing subduction angle is very large?
Yeah, so I did do a little bit of work in Baja a couple years ago, and we published a paper about similar stuff about helium carbon. Um, but I would love to look more into um, yeah, basically setting it up in a similar way. And I would love to learn more, Nick, if you have a chance to talk about like all the sampling opportunities in the Forearc. Um, I'm just trying to find the slide, like this slide. Yeah, where we were looking at all these features about changing subduction angle and how that's like a really interesting hypothesis to set up. Yeah, there was a paper. I was the lead author on it. I think it was like in 2020, and it was about helium carbon in Baja. But I'm sure there's way, way, way more work to be done. So, Nick, I'd be happy to talk about if you think there's good Forearc sites. That'd be awesome.
Thank you. And then we have a last question from Camilla who asks, or who says, thanks for the talk. I have a question about the carbon-14 signal, helium and neon ratio. Do you think that the signal would be repeated in a context where the crust is thinner than that of the Central Volcanic Zone?
Yeah, so it's about like this plot here where we're plotting radiocarbon activity versus the helium neon ratio. And the question is, I can't read this question, but would we see a similar feature if the crust was thinner? Is that the question?
Yeah, do you think this signal would be repeated in a context where the crust is thinner?
Yeah, I do. I don't think that this is unique to the fact that the crust is thick there. I'm assuming that anytime we measure helium, like every time we measure a helium isotope value, 3-4 ratio above like 1.8 or a helium to neon ratio above about 2, I think that's indicating that we're sampling deep source fluids. And I think that would be true irrespective of how thick the crust is. But we're going to test it, right? Camilla's going to measure that.
Exciting. Okay. Thank you so much for such a great talk and for these great questions. We hope to all see you at our next webinar in January. And thanks again, Peter, for taking the time today. I really appreciate it.
My pleasure. Take care,
Okay.
everyone.
Have a great rest of your day. Bye.
All right, you too. Bye.